Why would a locomotive that set speed records in Britain struggle to even complete a basic freight run in America? The answer reveals a fundamental truth about engineering. The best solution for one problem can be completely wrong for another. British and American locomotives didn't just look different, they were solving entirely different puzzles. When you look at a British locomotive from the Victorian era and compare it to its American counterpart, you're looking at two machines that seem to do the same job. They both run on rails, they both pull carriages, they both burn fuel to create steam. But that's where the similarities end. What we're really looking at is a perfect case study in how context shapes design, and how excellence in one environment can mean disaster in another. Let's start with something that seems simple on the surface: the track itself. Britain standardized on a gauge of 4 feet, 8.5 inches, a measurement that traces back to Roman chariot wheels. If you believe the popular story, America eventually adopted this same standard gauge, so you might think the locomotives would be interchangeable. But gauge is just one dimension of compatibility, and perhaps the least important one. The real difference was in how those tracks were built. British railway construction was, by necessity and tradition, a meticulous affair. When you're building through a landscape that's been inhabited for thousands of years, where every mile of track requires negotiating with landowners, where ancient property rights dictate your route, you build carefully. British tracks were laid on solid foundations, with heavy rails, proper ballast, and engineering that would last for generations. The railbed was stable, the alignment was precise, and maintenance was constant. American track construction was the complete opposite. When you're racing to connect the Atlantic to the Pacific, when you're relaying rails across territories where the surveyors are sometimes the first Europeans to see the land, you don't have time for perfection. American tracks were lighter, the foundations were whatever the local terrain provided, and the attitude was build it now, improve it later. Some early American railways were so hastily constructed that rails were simply laid on wooden ties placed directly on the ground. The tracks undulated, they shifted, they required locomotives that could handle imperfection. British locomotives, engineered for precision track, couldn't cope. Their rigid frames and tight tolerances meant they derailed on uneven track. Their suspension systems, designed to provide a smooth ride on stable rails, couldn't absorb the constant jolting of rough American roadbeds. It would be like taking a Formula One race car, designed for perfectly smooth asphalt circuits, and asking it to compete in an off-road rally. The precision that made it excellent in one context made it fragile in another. This brings us to a deeper philosophical divide: precision versus ruggedness. British engineering culture valued refinement. A locomotive wasn't just a tool. It was a demonstration of manufacturing excellence. Components were machined to exacting standards, parts fit together with minimal clearance, and every aspect of the design reflected careful optimization. British locomotive builders took pride in creating machines that were, quite simply, beautiful examples of the engineer's art. American builders had different priorities. They needed machines that worked, and kept working under conditions that would horrify a British engineer. An American locomotive might be hauling freight across the Nevada desert, where temperatures soared above 100 degrees, and then a week later be pushing through a Rocky Mountain snowstorm at 20 below zero. It might burn high-quality Pennsylvania anthracite one month and rough-cut cordwood the next. It might go 6 months between proper maintenance because the nearest qualified mechanic was in a workshop 500 miles away. So American locomotives were built with generous tolerances, with parts that could be hammered back into shape if necessary, with designs that assumed abuse rather than care. A British locomotive was like a precision watch. An American locomotive was like a sledgehammer. Both are tools, both are well designed for their purpose, but you wouldn't use one for the other's job. The loading gauge issue perfectly illustrates how historical constraints create incompatible solutions. Britain's railways were built around existing infrastructure. Tunnels had to fit under ancient bridges. Platforms couldn't encroach on medieval property lines. Clearances were tight because the railway had to squeeze into an already crowded landscape. This created the British loading gauge, the maximum height and width that a railway vehicle could be. British locomotives and rolling stock were designed to fit within this relatively compact envelope. America had no such constraints. When an American railway needed more clearance, they simply built it. Tunnels were larger, platforms were wherever they needed to be, and bridges were constructed to accommodate whatever size of locomotive the engineers could imagine. This meant American locomotives could be physically bigger, taller boilers, wider cabs, longer fireboxes, and size translated directly into power. Think about the implications. A British locomotive might have a firebox of 30 square feet. An American locomotive could have 50, 60, even 70 square feet of grade area. More firebox means more fuel burning, which means more steam, which means more power. British locomotives were operating at a fundamental physical disadvantage. They couldn't be made powerful enough for American service without being redesigned from the ground up to fit American clearances, at which point they wouldn't be British locomotives anymore. Fuel is another fascinating divergence point. Britain is, geologically speaking, sitting on massive coal deposits. The Industrial Revolution happened in Britain partly because coal was abundant, high quality, and accessible. British locomotives were designed with this reality in mind. They burned Welsh steam coal, which was nearly ideal for locomotive use, high energy content, low ash, consistent burning characteristics. The entire fuel handling system, from firebox design to ashpan configuration, assumed you'd be burning good coal. American railways faced a completely different situation. Yes, there was coal in Pennsylvania and West Virginia, but what about the railways pushing into Texas, into California, into the Pacific Northwest? Some of the most important railway routes crossed regions where coal simply didn't exist in commercial quantities. Early American locomotives in the West burned wood, cordwood, cut from whatever trees were available along the right-of-way. Later, they burned oil in regions where that made more sense. This required completely different engineering. Wood burns differently than coal, requiring larger fireboxes and different grate designs. Oil firing is a different technology entirely. British locomotives, optimized for Welsh coal, couldn't efficiently burn American fuels, and efficiency mattered enormously when you might be hundreds of miles from the next fueling stop. The terrain tells its own story. Britain is a relatively small island with gentle topography by global standards. Yes, there are hills, but there are no Rockies, no Sierras, no Appalachians. The steepest mainline grades in Britain were modest by American standards. British locomotives were designed to pull reasonable loads on reasonable gradients for reasonable distances. American railways faced challenges that would seem absurd to a British engineer. The Central Pacific Railway climbing the Sierra Nevada dealt with sustained grades of 2 to 3% while navigating tight curves and extreme altitudes. Southern Pacific crossing of the Tehachapi Mountains involved gradients where locomotives had to use helper engines just to move their own weight uphill. The grades on Saluda Hill in North Carolina reached more than 5% steep enough that trains had to use special braking procedures to avoid runaway accidents on the descent. British locomotives lacked the power-to-weight ratio for this kind of work. Their wheel arrangements evolved for British conditions, distributed weight in ways that made sense on flat routes but were wrong for mountain railroading. American engineers developed locomotive types specifically for these challenges: the prairie type for flat land freight, the mountain type for, well, mountains, the consolidation type for heavy pulling power. Each was optimized for specific American conditions that British designers had never needed to consider. Curves present yet another incompatibility. British railways, built through established territory with generous budgets, could afford to make curves gentle. Sharp curves required careful surveying, land acquisition, and often expensive earthworks to maintain proper alignment. British locomotive designs assumed relatively gentle curves would be the norm. American railways, especially in the West, made curves as sharp as they could get away with. Why? Because every extra mile of track cost money, and gentle curves meant longer routes. If you could save 10 miles by making the curves tighter, you saved the cost of building 10 miles of railway, which in mountainous terrain could be enormous. Some American branch lines had curves so sharp they approached the theoretical minimum radius that flanged wheels could navigate. British locomotives, with their long, rigid wheelbases, couldn't handle these curves. They'd derail or bind up wheels, scraping against rails. American designers solved this with innovations like the leading trucka pivoting assembly under the front of the locomotive that could swing to follow curves while keeping the driving wheels on track. They developed articulated locomotive types, where the entire engine could flex around curves. British precision engineering, ironically, worked against the flexibility needed for American conditions. The economic equation was straightforward and brutal. A British locomotive represented hundreds of hours of skilled craftsman labor, precision machining, and quality materials. It was expensive, reflecting British manufacturing standards and labor costs. If you bought a British locomotive for service in America, you were paying a premium price, then paying shipping costs across the Atlantic, then facing the reality that spare parts would need to come from Britain as well. A broken driving axle might mean weeks of waiting for a replacement to arrive by ship. American mass production, by contrast, drove costs down. Baldwin Locomotive Works, the American Locomotive Company, and others built standardized designs and quantity. Parts were interchangeable, not just within a locomotive type, but often between different builders' machines. A railway in Colorado could wire a workshop in Pennsylvania and have a replacement boiler tube, driving rod or valve assembly shipped west by rail in days, not weeks. The entire industrial ecosystem was designed around domestic production and rapid supply. Maintenance philosophy reflected these economic realities. British railways could afford regular preventive maintenance because their compact geography meant locomotives were never far from a proper workshop. British practice was to schedule frequent inspections, replace parts before they failed, and keep locomotives in optimal condition. This required skilled mechanics, specialized tools, and well-equipped facilities. American railways adopted what we might call a run-to-failure approach. Locomotives were worked hard, sometimes around the clock, until something broke. Then they'd be patched up with whatever resources were available, sometimes trackside, sometimes at a basic shed facility, occasionally at a proper workshop if the problem was serious enough. This wasn't negligence. It was rational response to circumstances. When you're operating across continental distances with limited capital, you can't afford British-style maintenance intensity. British locomotives required that intensive maintenance to function properly. Their tight tolerances meant that small amounts of wear would cause problems. Their complex valve gear needed regular adjustment. Their precision-machined components couldn't tolerate the heavy-handed repairs that American practice assumed. A British locomotive in American service would quickly deteriorate, under treatment that American engines handled routinely. The speed versus power trade-off reveals different priorities. British railways, serving a nation where cities were relatively close together, emphasized passenger service. Speed mattered because reducing journey times between London and Manchester, or Birmingham and Edinburgh, directly improved service quality. British locomotive designers optimized for speed, creating streamlined designs with large driving wheels and relatively light adhesive weight. American railways prioritized freight. The economic justification for most American railways was hauling goods timber from forests, minerals from mines, grain from prairies, manufactured goods to markets. Passenger service was important, but freight was the foundation. American locomotives were designed to pull heavy loads over long distances, even if they couldn't match British passenger engines for speed. A British Express locomotive might sustain 70 miles per hour with a light passenger train on flat track. An American freight locomotive might lumber along at 30 miles per hour, but could pull twice the tonnage up at 2% grade. Safety equipment differences were more than cosmetic. American railways operated in conditions where livestock wandered across tracks, where level crossings were common, where trains might encounter debris on remote stretches of line. The iconic cowcatcher was essential for pushing obstacles off the track before they could derail the locomotive. Bright headlights were necessary because trains ran through wilderness without line-side lighting. Bells warned workers and animals of an approaching train. British locomotives lacked these features because British conditions didn't require them. British railways were fenced, crossings were controlled, livestock didn't roam freely near tracks. Installing American-style safety equipment on a British locomotive would add weight and complexity without providing meaningful benefit in British service. But without that equipment, British locomotives were actually dangerous in American conditions. Even coupling systems diverged. Britain standardized on buffer and chain couplers, which worked well for British practice. America adopted the knuckle coupler, which allowed for remote coupling and uncoupling essential when you reassembling 50-car freight trains in a remote rail yard. These systems were incompatible. A British locomotive couldn't couple to American rolling stock without adapters, and even with adapters, the different buffering systems meant they didn't work together properly. The cultural dimension is perhaps the most subtle, but also the most important. British engineering culture valued incremental refinement of proven designs. When something worked, you made it better through careful evolution. This produced excellent results within established parameters. British locomotives at the end of the steam era were magnificently refined machines, representing over a century of continuous improvement. American engineering culture valued radical experimentation. If something might work better, try it and see what happens. This produced some spectacular failures, but also rapid innovation. American designers weren't afraid to completely abandon a design approach if something new looked promising. This willingness to experiment meant American locomotives evolved much more rapidly to meet changing conditions. Neither approach was inherently superior, but the American context rewarded experimentation. When you're building railways into territory no railway has ever crossed before, when you're facing problems no one has solved before, you need designers willing to try completely new solutions. British conservatism, which served British railways well, couldn't keep pace with American needs. Scale of operations completes the picture. Britain's longest main line from London to northern Scotland is about 400 miles. Many British railways operated profitably, with routes of 50 to 100 miles. Locomotive design reflected these distances' reasonable water capacity. Coal bunker sizes calculated for journeys, measured in hours rather than days, maintenance intervals assuming frequent returns to base. American transcontinental railways covered 2,000 miles. Branch lines in the west might run 300 miles through empty territory before reaching another town of any size. Locomotives needed to operate for extended periods far from supply bases. They needed larger water tanks, bigger coal bunkers, designs that assumed days of continuous operation between proper servicing. So we return to our opening question. Why would a locomotive that set speed records in Britain struggle in America? Because it was solving a completely different problem. British locomotives were optimized for a compact, established railway network, operating in a temperate climate with abundant coal, skilled labor, and regular maintenance. They were excellent machines for those conditions. American locomotives were optimized for a vast, developing railway network crossing every type of terrain and climate, operating with whatever fuel was available, maintained by whoever was available, built to survive rather than to impress. They were excellent machines for those conditions. This isn't a story of British failure or American triumph. It's a demonstration of how technology is always contextual. The best design is the one that best fits its environment. British and American railways diverged because they faced fundamentally different challenges. Both traditions produced innovations that advanced railway engineering worldwide. Both solved their respective problems brilliantly, but they couldn't swap solutions because the problems were different. A British locomotive in America was a precision instrument trying to do a sledgehammer's job. It was a racehorse entered in a plowing contest, not because it was poorly designed, but because it was designed for an entirely different world. That's the real lesson here. Engineering excellence is never absolute. It's always relative to context, to constraints, to the specific problem being solved. The British built perfect locomotives for Britain. The Americans built perfect locomotives for America. And never the twain shall meet because they were never meant to.